understanding, in essence, the role of diet in health, developing foods for the next century for health, and creating value for agriculture itself. So the big opportunity, of course, is disease prevention. Sounds wonderful, but how are you actually going to do it? What prevention means is you're literally going to make healthy people healthier. You're not going to wait till they have a disease and diagnose and treat. You're actually going to make healthy people healthier. And therein lies the challenge. So we're using literally the resources that have established over the past decade in genomics. You are literally in Genomics Central. University of California, Davis has more genomes than any other campus in the world. And it's the breadth of genomes that's remarkable. Viruses, bacteria, yeast, molds, insects, plants, animals, humans. It's the great diversity of genomics that makes Davis singular. And we're taking advantage of that to ask a very simple question. What evolved under constant Darwinian selective pressure to be nourishing? So we're taking all of this literally genomic information of the entire phylogenetic tree, from simple organisms up to humans, and ask, okay, what can they tell us about prevention? The good news is we have a full repertoire of genomes across the phylogenetic tree. The bad news is it's a war out there. The vast majority of organisms have been constantly evolving to avoid being eaten, and they're good at it. So if you're looking for ways to be toxic, to prevent yourself from being eaten, evolution can really tell you that. But there really isn't much selective pressure on foods that would be good for you. In fact, there's really only one: lactation. This remarkable process that came along very late in animal evolution, wherein the mother literally dissolves herself to make a comprehensive diet for her infant. And that's our model. The mother-infant pair. Mother dissolving herself to produce milk for the infant. Everything costs the mother. If it doesn't improve the health of the infant, then it's under negative selective pressure. It'll be lost to evolution. But if anything in the milk improves the health and competitive advantage of that infant, it's under very strong positive selective pressure. And remember, milk is improving the health of a healthy infant. So we have had a Darwinian engine developing mechanisms of health and prevention generation after generation for 200 million years. And that's our model. So we call it our Rosetta Stone for understanding diet from this larger and mechanistic perspective. I want to give you a couple of examples of illustrating what is teaching us about diet and health and how we can apply it to a broader audience. So remember the model. Mother's dissolving herself to make it. If it's not good for the infant, it's going to be lost to evolution. Well, imagine our surprise to find out that in human milk, the third most abundant solid component is completely undigestible by the baby. It goes right through them. This was really a gobsmacking moment. Why would mothers be putting undigestible matter into milk for babies? So, being at UC Davis gives you wonderful access to the best scientists in the world. Carlito Labriglia is the best analytical chemist in the world at complex conjugate molecules. He develops analytical platforms to study molecules like we've discovered. And it turns out the molecules that are undigestible are complex oligosaccharides, biopolymers of sugars in very stereospecific arrangements. Carlito can measure every single one of them in high throughput. So if we know what they are now, then the question becomes, why? Why would mothers put undigestible material into their milk? So the first idea was, well, it's not feeding the baby, it must be feeding bacteria. So we enlisted the help of David Mills, a world-famous microbiologist in the Food and Wine program. He studies microbial ecosystems. The ecosystems of bacteria in wine and the ecosystems of bacteria in the human intestine. We isolated the oligosaccharides with the help of the engineering department and gave the oligosaccharides to David Mills. Did the bacteria grow on them? No. He tried bacterium after bacterium after bacterium. Bacteria, in fact, don't grow on these oligosaccharides. And then he found it. Oh, what a surprise, in the intestine of breastfed babies. He sequenced the entire genome of this bacterium. It's a very narrow subset of Bifidobacteria longum, termed subspecies Infantis, and mapping all of the oligosaccharide linkages in the complex oligosaccharide, David mapped genes in Bifidobacteria encoding glycosidases. And the linkages in the oligosaccharides matched one by one to the oligosaccharide hydrolyzing gene products in the bacteria. Clearly, your mother is recruiting another life form to babysit her baby. And she's making sure only that bacteria can thrive by making sure the only food available is something that only this one can ingest. So now we have this remarkable lesson from evolution. Now we're bringing it to practice. Now remember I told you that Carlito Labriglia built a platform so we can measure high throughput oligosaccharides in milk. That same analytical platform can measure the oligosaccharides going into a baby and coming out of a baby. This is a poopogram. These are the oligosaccharides coming out of a baby, a single baby, through the first weeks of lactation. And you notice for the first couple of weeks, the oligosaccharides come in and the oligosaccharides go out. Now, if you measure the bacteria in the baby at exactly the same time, what you have is a wide range of rather unpleasant bacteria that the baby has acquired during the passage through the birth process. So there are various proteobacteria, coliform, clostridia. But you notice, as the oligosaccharides begin to disappear from the baby, up comes Bifidobacterium Infantis. And in fact, after a couple of weeks to a month, depending on the baby, the diaper of a breastfed baby is 50% by weight this one bacterium. It is just chock-a-block full of one bacteria. In fact, we probably should have just asked fathers. Fathers will volunteer to change the diaper of their baby as long as it's breastfed. The minute you wean it, whoa, what have you done to my baby? It's the bacterial population. It's changed completely. So, we've begun to study systematically what are the implications to the baby of having this unique microbiota. For example, in studies with Helen Raybould, one of the remarkable things that this bacteria does is promote the closure between cells in the intestine. It literally closes the barrier of the intestine to foreign substances. So it's assisting the baby in establishing in essence, a molecular type barrier. But it goes beyond that. All of those aspects we thought were anti-inflammatory, and we've shown again and again these bacteria are helping the baby avoid inappropriate activation of the immune system. So they're in essence lowering activation and inflammation in the baby. But there was a worry. Lowering inflammation is a current target of pharmacology. They would love to lower inflammation, and many therapeutic and biotherapeutic strategies have emerged. In every case, when you lower inflammation, what you're doing is suppressing immunity, lowering the activity of the immune system, and there are side effects. You are much more susceptible to infection. So the consequence of pharmacological intervention in inflammation is to lower inflammation by lowering the immune system and increasing the risk of infection. You're dampening the immune system entirely. So we were worried, what would this Bifidobacterium Infantis do to the immune system of the baby? Does lowering inflammation inevitably carry with it the consequences of lowering the ability of the immune system to respond? So it turns out that we could test that in vivo. Charles Stevenson was recruiting a large cohort of babies in Bangladesh that had all been born by cesarean section, and he was testing whether or not nutritional intervention would alter the response to vaccinations. It did not. But he had a large cohort of controls that had varying amounts of Bifidobacterium Infantis because of C-sections in which he could test is Bifidobacterium infantis colonization of a breastfed infant consistent with lowering vaccination response or increasing it? It's increasing the immune system surveillance. You get better, more abundant, and robust response to vaccination when Bifidobacterium infantis is present in babies. It's simultaneously lowering inflammation and increasing the activation of the immune system appropriately. So, and in fact, this is all consistent with the mechanisms that we're showing in the gut for infants. In fact, Helen Raybould is showing that the bacteria are communicating through the neuroendocrine cells in the gut all the way to the brain, regulating immunity, various metabolic processes, even neurological development. So this population of bacteria in the infant is protecting it and enhancing its development and performance. So we have now a completely different model of evolution. The evolution of mammals has been the combination of mothers, infants, and this remarkable microbial system. So we're bringing it to practice already. Who would really need this? Well, breastfeed babies. Breastfeed, breastfeed, breastfeed. But imagine a cesarean section premature infant in the neonatal intensive care unit. Cesarean section, sterile birth, it doesn't get the bacteria. It's in an incubator, it's not getting any oligosaccharides. It is going to acquire bacteria that will, in essence, colonize and stay with the intestine of that baby for the rest of its life. And where is it getting them from? The hospital around it. This is not the way you want to start life. So with Mark Underwood, who's the head of neonatology in the medical center, he is now giving his babies in the NICU the combination of the right bacteria and the right oligosaccharides. They start life with a microbiota that's exactly the same as a breastfed infant. So we've now begun to apply this much more broadly. Who else could take advantage of these mechanisms? If you get the bacteria in your population, in your microbiota right, you get all sorts of protection. Is this valuable for other stages of life? So we have a large program sponsored by the Office of Research here at University of California, Davis, where we've recruited all sorts of scientists to understanding the role of the microbiota in various aspects of protecting a damaged gut and using the strategy of this Bifidobacterium infantis and combined with the right oligosaccharides to protect that. And we've seen time after time, chronic infection, from viral infection of HIV to bacterial infection. Getting the right bacteria in the intestine is highly protective. So, how does it relate to cancer? Well, two elements of cancer initiation and promotion are associated with inflammation and bile acid metabolism. I'll just go through them quickly. The gut is responsible for a lot of the inflammation that's systemic in individuals. So a variety of toll-like receptors literally decorate the gut. Molecules from food and the diet and bacteria will activate those receptors and promote the activation of the immune system, including inflammation. Bifidobacterium infantis lowers this signaling. Pathogens in the microbiota. We all harbor a significant number of pathogens. It's a chronic infection, basically. It's usually asymptomatic. Nonetheless, they're all there, and they're chronically stimulating the immune system to deleterious effects. That's exactly what Bifidobacterium infantis gets rid of. The barrier integrity of the intestine is constantly under threat, and again, infection and chronic infection by bacteria can weaken those junctions and compromise the barrier function. And Bifidobacterium infantis displaces bacteria and strengthens the barrier function in the gut. And finally, inflammation can be in a variety of other ways. And one of the newest forms of inflammation is that associated with obesity. The excessive size and recruitment of immune cells into adipose tissue has become a new source of systemic inflammation. And lo and behold, Bifidobacterium infantis regulates metabolism, food intake in babies, and when the same bacteria is applied to an overweight mouse model, the mouse model begins to approach a more normal metabolism and reduces obesity and the inflammation associated with it. So, Bile acids. It's now clear that the bile acids that are produced by your liver into your bile represent a very interesting signaling system systemically. So you place them into the intestine, they assist with the absorption of fat-soluble molecules, but then they go in the intestine, and conjugated bile acids are acted upon by the bacteria, and then they're reabsorbed. And that portfolio, that constellation of bile acids, then signals all the way back through the body. And some of them are toxic. And so bile acids that are deconjugated by bacteria in the intestine promote toxicological inflammatory processes. And with Yvonne Wan in the chemistry program, we're now studying the role of the replacement of deleterious bacteria with beneficial bacteria to stop this process. So, in fact, evolution is providing us with remarkable mechanistic insights, how you can control inflammation not at the expense of suppressing immunity, how you can monitor and control metabolism, from obesogenic properties to bile acid metabolism. And remember, milk is teaching us the targets and mechanism of action. They act as ingested substances, and they have a safety dossier for your dreams. They're going into babies all day, every day. So, thank you very much.
After a question, I'm sure there are many questions.
Sure.
There's been some serious allergic reaction to Bifidobacterium, right, to humans, at least for adults.
Actually, the number of bifidobacteria is much wider than people had previously realized. Modern sequencing methods, genomics, have revealed that bifidobacteria as a group of bacteria is actually widespread. It's in a variety of ecosystems, and if we take Bifidobacterium longum, subspecies Infantis, the one that is in essence co-evolved with humans, the difference between it and other Bifidobacteria in other locations is not trivial. David has found 20% difference between the genome of Bifidobacterium Infantis and Bifidobacteria in, for example, adults. 600 genes difference. So the old idea that a bifidobacteria is good for you, or a lactobacillus probiotic is good for you, it's not nearly specific enough. The future of microbial intervention in the microbiota is going to be very strain specific. And if you don't get the strain specificity right, you don't get the growth as a result of the very specific oligosaccharides, and you don't get the benefits. Thank you.